Okay. So we're going to start with the octet rule. What does the word octet mean? 8. Okay. And you already know this from the ionic compound unit, also unit 2, I think a little bit. What's the significance of 8? 8 what? What kind of electrons? 8 valence electrons, right? Meaning what? Like, so that's the right thing. We're talking 8 valence electrons. Say more. What does that mean?
There's 8 electrons on the outer shelf, and those are what get bonded to a new atom.
Okay. All atoms want 8 valence electrons. Valence electrons are electrons in the outer energy level, right? See, we're reviewing unit 2. And the reason they bond is to achieve 8, right? Okay. Now, the only thing I'm going to say there is that like 8 is the most common number, but they don't all necessarily need 8. What they really need is a complete outer energy level. And if you're ending in energy level 2, 3, 4, so on and so forth, 8 is the magic number. But if you're ending in energy level 1, which not very many of them do, but hydrogen does, what's the magic number for that energy level? 2, because there's only one S, right? And one S can only hold 2 electrons. So the main important thing is that the outer energy level needs to be filled, okay? And for 99% of the elements, that means the outer energy level has 8 valence electrons. For a couple elements that end within the first energy level, it means they only have 2. Okay. All right. So that's the first thing. All right. Molecular compounds, which you might, yeah, do you have a question?
Yeah, the noble gases of 8 valence electrons.
The noble gases naturally have 8. Great question, except for helium, because helium has 2. But the noble gases naturally have 8, which is why they don't really bond as much as everybody else, really at all, to be honest. A couple of them bond a couple different ways, and you'll learn about that in this unit. And really it's just them being generous. It's not actually them needing to bond. It's just them being like, all right, sure. Yeah, I'll do that. Okay. So we'll talk about that. So great. I'm glad you brought that up. Okay. So molecular compounds have covalent bonds. What types of bonds do ionic compounds have? Ionic bonds. That name's easier to remember because it matches the compound type. But you've got to remember molecular compounds have covalent bonds. All right, let's talk about ionic bonds for a second because we did this a lot in Unit 3. Talk to me about how ionic compound, talk to your partners. How do ionic compounds form? Like, let's be very specific. What has to happen for an ionic compound to form? Okay, take a minute and try to remember that with your partner. So ionic compounds come from cations and anions. Cations are positive, anions are negative. How do you make a positive ion? What has to happen?
To remove 2 electrons from the outer shell, to like get closer to 8.
Right. So, and what types of elements make cations? Metals. Okay, so it's all coming back, right? Okay, so metals form cations by losing electrons, right? So I'm going to put my electron down. Okay, now because I've gotten rid of that negative electron, I'm positive. Okay, now how do we make negative anions? You gain electrons. Okay, so what happens is if I'm a metal who wants to, so like I'm going to have my right hand, because to you on the screen it looks like my left. If I'm going to have this hand be a metal, it's a cation, like it's going to want to lose this electron. Let's say I'm sodium. I have one more than neon, right? Remember, I end in 3s1. Neon has 2p6. It has that 8 valence electron thing that I want. What's the easiest way for me to be like neon? To get rid of this electron. Okay, well then this hand can be fluorine. Fluorine's number 9. Where does that end? 2p5. Fluorine also wants to be like neon. What's the easiest way for fluorine to be like neon? To gain an electron. So now the electron that my sodium wants to lose goes to fluorine, right? This is now positive. This is negative because it has the extra electron, right? And then what do positives and negatives do? They attract, okay? So ionic bonds, which we studied in all of Unit 3, just as a reminder, they are essentially a transfer of electrons from the metal to the nonmetal. The metal wants to lose to get 8. The nonmetal wants to gain to get 8. Once that transfer occurs, you have a positive ion and a negative ion, and positives and negatives attract intensely. Okay? So what holds ionic compounds together is the intensity of that attraction, because positives and negatives are extremely attracted to each other. So they actually get as close together as they possibly can. Imagine them like shoulder partners whose shoulders are constantly touching. Okay, that's what an ionic compound is. And what state of matter do they all come in? Solids. And the reason that they all come in solids is because they're all really close together. And the definition of a solid really is that the particles don't move, right? They're all stuck together. And so because they're shoulder partners that are literally touching, stuck together, that is why they are all solids, because none of the particles move. Okay? So that's how ionic compounds work, just as a refresher. They involve metals and nonmetals. What types of elements do molecular compounds involve? All nonmetals. And what are all nonmetals looking to do to get 8 valence electrons? They're all looking to gain. So is anyone going to be up for transferring their electron to somebody else? No, nobody wants to give up an electron. This is why molecular compounds are different. Nobody's willing to like really let go. Like, okay. But they have some options because they all still want 8. So they have to get a little bit creative about what they're going to do. Okay. You can relate to this option. Have any of you like had to stay after school for something, maybe like a late practice or a late rehearsal, but you're hungry, and so you decide with your friends that you're gonna like walk to Mr. P's? Okay, I know I've seen some of you do it. Okay, and you know, maybe you're gonna get a pizza that you're all gonna share. Okay, what's gonna be your first, like, what's the first hurdle that you have to figure out before you get a pizza from Mr. P's? How much is it? Okay, how much money it's gonna cost, right? But secondly, there is actually a very specific hurdle that's very convenient for me related to Mr. P's. What is it? They only take cash, okay? And we pretty much live in a cashless society at this point, right? So if you're gonna actually go get pizza from Mr. P's, like you're gonna split a pizza with your friends, you're gonna have to figure out who has cash on them, right? Because they're not taking Apple Pay, they're not taking a debit card, right? Like you're gonna have to figure out who has cash on them. Maybe one of you does. Okay. So, or maybe a few of you do. What do you do to figure it out? Like, how do you handle this? How do you figure out how and who is going to pay for the pizza? What do you do?
You have the one person that has cash pay, and they say I'll pay you back after.
Okay, so maybe the person who has the actual cash pays, and then the friends do what? What are some options?
Payback.
How? Yeah, maybe you're gonna Venmo, right? How many of you have done that? Venmoed your friend on the spot, right? Like, okay, yeah, that's an easy way to do it, right? What if somebody has like $20 and somebody else has like a 5 in their pocket? What are they gonna do? What?
You put them together.
Yeah, you're gonna give the person who has the $20 the $5, right? What if there's only 3 of you splitting the pizza, not 4? Then the pizza costs $20. Should we give the person paying 5 less pizza than we gave the other 2 people? Do you do that? Probably not, right? Like you're just gonna eat. You're not gonna like make a big deal of it. If somebody only has $1, one of your friends has no money, are you gonna be like, sorry, I know you're hungry, but you're not eating today? Are you gonna do that to your friend? No, probably not, right? So all of you are hungry. All of you want pizza. Sounds like a great idea. You're all gonna walk to Mr. P's, pool your money, get your pizza. You're gonna eat. Some of you are gonna contribute more than others, right? But ultimately, you're all gonna get fed, correct? That's what covalent bonds are. Covalent bonds are pooling all the valence electrons because nobody has enough. So we're going to pool all the valence electrons and we're going to figure out, okay, how can we use all these electrons to make sure that everybody gets 8? Okay, so they share their electrons. It's not a transfer. It's all right, we're all going to have part of this electron, just like you're all going to have part of a pizza. Okay. So they share electrons to meet the octet rule for all the nonmetals. Okay. And we can draw what they do with their electrons with something called the Lewis structure, which is showing how the sharing actually occurs. Okay, so that's what we're going to move on to next. Is we're going to do an example very, very slowly, and I'm going to use it as an opportunity to review. So the first thing I would like you to do with this F2 example that we're going to use is I would like you to write the electron configuration for fluorine right there. Right? The electron configuration for fluorine, please. Okay. So, yeah, as most of you had, the configuration for fluorine is 1s2, 2s2, 2p5. Okay. Go ahead and highlight the valence electrons. Which electrons in this configuration are valence?
The people.
The big 5. Is that it? And which 2?
And yeah, so it's two.
Okay. Why are both of those part of the valence electrons?
That's the second.
Yeah, because remember, you're looking for your biggest number, okay? But your biggest number is in 2 places, okay? So you have 7 valence electrons because it's 2s2, 2p5. Now, just to remind you, you don't have to write out a configuration every time you want to figure out valence electrons. You already know how many do the noble gases have? 8. Fluorine is right next to neon. So that means if neon has 8, fluorine must have 7. Okay. Also, what group number is fluorine in? 17. And remember, the second number of that group number tells you the valence electrons, right? So group 17 has 7 valence electrons. Are you starting to remember some of this? Okay. All right, good. So here is the part where I want you just to watch. Okay, so do me a favor. Stop touching your iPad. Look up here, engage your brain. Let's talk about this. So if fluorine has 7 valence electrons, okay, and I just want you to watch, I'm going to give you a chance to draw in a little while, but focus on what I'm saying, not copying what I'm doing. I'm going to make a box, a square, around fluorine, okay? I'm actually going to erase it in a little bit, but I think it's helpful the first time to use it, okay? So we've said that fluorine has 7 valence electrons. I'm going to draw them around this fluorine. 1, 2, 3, 4, 5, 6, 7. Okay, so I drew that box around fluorine because I want you, when you write down the element symbols, I want you to think of it as like the letter itself having a top, right, bottom, left. Okay, and so you're putting your dots around the, each dot represents an electron, and you're putting your dots around that symbol in an organized fashion. Okay, and you'll notice that I did like, I went 1, 2, 3, 4, 5, 6, 7. Did you notice that? I didn't do pairs. I didn't go 2, 4, 6, 7. I went 1, 2, 3, 4, 5, 6, 7. Okay. All right. So that's what a Lewis structure, I'm going to erase the box now, and I'm going to actually erase my dots and draw them closer. That's what a Lewis structure for fluorine actually looks like, okay? So you would show the valence electrons like that, okay? All right, but how many fluorines do we have here? 2. So I'm going to draw another fluorine right here, okay? And this one I'm going to give red dots. So 1, 2, 3, 4, 5, 6, 7. Okay? All right. Now, do either of these have 8 valence electrons? No, they don't. Does anybody want to give an electron to the other fluorine? No, they don't. So what are they going to do? They're going to do what you and your friends do related to getting a pizza from Mr. P's. They're going to cozy up to each other and pool their resources. They're going to pool their electrons. They're going to say, well, wait a second. If, I have 7 and you have 7, and we let these unpartnered ones partner up, it kind of makes me feel like I have 8, right? This fluorine, 2, 4, 6, 8. This fluorine, 2, 4, 6, 8. They're sharing electrons now, okay? And the way that works, because there's something else I want to draw for you, okay, so that you understand. So realistically, okay, keep in mind we have 2p, 1, 2, 3, 4, 5. Let's see if I can do this correctly. It's always a little tricky. And also I'm doing it backwards, but it really doesn't matter. When I say backwards, I mean my black and red is like the opposite of left and right. Watch, here's what's happening. They're overlapping, if I can do this. They're 2p orbitals. Okay, do you see how that just worked. They took their 2p sublevels that had 5 valence electrons each, and they let them share space, meaning overlap each other, so that they feel like their outer energy level is full. Okay? And that's how that works. All right? But we don't draw it like this exactly. Okay? What a Lewis structure actually looks like is this. Okay, what did I change there?
So each of them have a valence electron. Side and each side.
Okay, on the right track. Let's see if we can explain that in a different way. The line is the big change, but what is the line representing?
A molecular bond.
It's representing a covalent bond, right? And what are covalent bonds? What are they doing with electrons? Sharing. So that line right there, okay, represents a shared pair of electrons. Okay, so what do dots represent? They all represent valence electrons, lines and dots. What kind of valence electrons? If this is a shared pair, right, dots are unshared pairs, right? Okay, and you'll notice, how are we, like, all of them are represented in pairs, correct? Because how many electrons go in each orbital? 2, right? They're paired up typically. Okay, so a pair of dots represents an unshared pair of electrons, and a line represents a shared pair. Okay, so here's what I'm going to tell you to do now. That was a lot of information. I am going to tell you to copy this down now, but hold on. I'm going to ask you to go one step beyond copying it down. Maybe write a sentence or two of something I said that was helpful beyond what I drew up here, that helps you understand it a little bit deeper when you come back to read it later. Okay, so write a sentence or two explaining this to yourself a little bit more, or writing some helpful hints down.